Assalamu alaikum. My name is Mubin Malik, and the purpose of today's video is to give some explanation and simulation of a line follower robot that we were assigned to make in our DLD theory and DLD lab project. So what is a line follower? I will tell you after I tell you about the combinational logic on the basis of which this robot was designed. So a combinational logic is a logic that involves the use of Boolean circuits without the dependency on time. Combinational logic differentiates from sequential logic on the basis that combinational logic does not have memory involved with it. So this is basically a block diagram, and the combinational component that we used in this circuit was an 8x1 mux. I will tell you about it in a bit, that how and why we chose that particular IC. So this is basically a block diagram explaining to you how this robot was actually working. So this block represents two multiplexers, one for each left and right motor. Each multiplexer is receiving inputs as from the left sensor, right sensor, center left sensor, and center right sensor. So these four inputs go into the mux, which gives output directly to the motor drive module. The motor drive that we used was L298 H-bridge motor drive, and that motor drive basically drives the left and the right motor. So after this block diagram was designed, we had in mind that how we were going to move forward. So these are some of the components that we used: two 8x1 muxes, four IR sensors. IR sensors are the integral part of our line follower robot, because that sensor is going to detect the black and white on the arena, on the basis of which our car or the robot will follow the line. These were the components. This is the car kit that we used to make it run on the arena. This was some of the assembly procedure, and this was our arena provided to us by our university that we had to follow and use. This is the 74151, which is basically an 8x1 mux. It has 8 inputs and 1 output, which is the characteristic of a multiplexer. These are the IR sensors. So you can see that there are 2 LEDs on each sensor. There's a trimmer capacitor, and basically it's a potentiometer, and it has 3 pins. So this white LED emits out infrared light that bounces off an object and is then detected and received by this receiver. This potentiometer helps adjust the range of the IR sensor, and these 3 pins, VCC and ground, basically power up this sensor, and the output is the pin that gives out the binary output in the form of 5 volts. So after that, this is the L298 motor driver. This is basically the L298 IC. These are some capacitors and voltage regulators. So it has 3 pins. This is the 12 volt input pin, the center pin is the ground pin, and this pin is the output 5 volt. So after this motor driver, this is basically some pin out of the IR sensor I have explained you earlier, and this is the lithium battery that we use. This is a 3.7 volts battery, and it has a high current discharge, which is ideal for which is ideal for this type of motor drivers and the circuits. This is the simple DC motor that we used, and this is a battery operated, and it works by simple DC voltage. This will be driven by our motor driver, and these are some of the specifications you can find in the report. And this is the 74151 MUX. Actually, this is its actual IC, and this is what its block diagram looks like. So I will explain to you about its block diagram. These are the 8 input pins, and these are the 3 selection lines on the basis of which the input to be shown at the output will be selected. So if I give 0 0 0 at the selection lines, then the input connected to the output will be this X naught. This X naught will be connected to a Y, and this Y bar is basically the inverse of Y. Whatever will whatever the logical output at Y will be, the Y bar will be inverse of it. So if Y is 1, then Y bar will automatically be a 0. So if I give 0 0 and 1 at the selection lines, then the input connected to the output will be the X1, which is the second input. This will be connected to the output. This is the pinout of the 74151 IC. The 16 and 8 pins are the power pins, and all the other pins are labeled. This is the actual output that we are going to use. These are the 3 selection lines, and this pin number 1 2 3 4 and 11 12 13 14 and 15 are the 8 input pins. So this is the pinout of 74151. This is the NOT gate that we are going to use if we are ever going to need an inverted input for our circuit. So this is the pinout of our motor driver. I have explained earlier. I have given you the complete representation of it. So this is our simulation in the Proteus. I will show you again, and I will run the simulation for you after I have explained my truth table to you. And this was the schematic design on the basis of which our PCB was designed. So this is our truth table. This is basically the most integral part in the build of this line follower robot. These 4 inputs are basically representing our 4 IR sensors that I have shown you above. They are in the form of an array. So if we look at the robot from the top, the right sensor will be on the right and the left sensor will be on the left, as quite rightfully. So as we know that there are 4 inputs, so these 4 inputs can make 16 combinations, because 2 raised to the power of 4 is 16. So we can have 16 unique and distinct combinations from these 4 sensors. Now for each combination, what our output should be is basically the thought process behind the design of this line follower robot. So if you can see this combination right here, 0 0 0 and 0, both sensors are 0, which means that that all these sensors are on a white line and they are reflecting the light, infrared light, back at the sensor. So this means in the sensor logic that whenever the light is reflecting from a white surface, the sensor gives out 0, but whenever the sensor detects a black, it gives out a 1. It gives out a 1. So for this first combination, you can see that there are 4 zeros, so all sensors are on the white. So now for my design, I have selected that in this condition both the motors should be off. Next condition comes when the right sensor, the most right sensor, is on a black line, so which means that the black line is going towards the right, so the robot has to move towards the right, and the left motor should be on, because this works on the same principle a tractor or an excavator works. So if you have to turn the robot towards the right, you have to turn the left motor on. So this case is depicted right here. Same goes in this case. in this case the center right sensor is on the black line. I have chosen this condition to be in which the robot moves forward. So both these motors are on. In this case, the right sensor has been given the priority, so the motor, only the left motor will be on, and the robot will move towards the right. Now all the other cases you can see in this truth table are basically a depiction of all the previous cases. They are a mirror or a silhouette of the previous cases, except for these some unique cases which are basically impossible to achieve theoretically, but practically there is a slight chance that these types of conditions may get involved in our robot, because there can be some issues in the calibration, there can be some issues with the sensor. So this condition can actually be a 011, like if I tell you about this condition actually can be a 0110, but sensors, the calibration of the sensor may cause them to make a 0101. So these types of condition have to be dealt with. So I have assumed that if ever this condition comes, the robot should be given the priority to the right sensor and the left motor should be on. Now this condition in which both these two sensors on the black line is quite understandable, that the robot has to move in the forward direction only, and if three of the sensors are on, then I have to give the priority to the most directional sensor. I call these sensors the directional sensors, left and right, because these are the sensors that are actually giving us the sense in which direction the robot will move. So this was the truth table. Now as you can see, there are multiple ways in which we can solve our truth table, and we can devise a logic on the basis of these outputs. The method I have used is the 8x1 mux. Now a question might arise that if there are 16 possible combinations, how can you divide that to an 8 input mux? So this is done on the basis of the rudimentary logic. What rudimentary logic is? Rudimentary logic basically divides a single output. You can see it divides these two outputs into a single one. So it will combine basically these two outputs of the left motor and right motor into a single output. And if you can see here for the left motor, if I combine these output, this basically follows the right sensor. So in this table again, I have clarified that how the rudimentary logic is made. I really apologize for this truth table because I mistakenly put this column right here instead of here. So if I tell you this column is basically for the right motor and this column is basically for the left motor, and how does this logic work? We have to combine two outputs into a single one. So if I combine the first original two outputs into a single one, you can see that this 0 and this 1 are actually following the rightmost sensor. So whatever the right sensor is giving, you can get it at the output. So we can say that these two combinations are basically R. Same goes the case here. No matter what the value of R is, the left motor is giving a 1. So we can see that we can say that this is a permanent high. Same is the case here and here. Now the next, you can see down right here, we have a permanent 0, which is shown right here, again and again. So you can see that 16 of these outputs are reduced to 1, 2, 3, 4, 5, 6, 7 and 8 outputs. Now if we see for the right motor, you can see the first combination is a 0, that is a permanent 0. It is not depending on any of the sensors, so you can see that this is a 0. For the next case, whenever the R is 0, the output is 1, and when the R is 1, the output is 0. So we can say that these two outputs are basically following the R complement. So we have written R complement right here, and this goes on for the whole column. So again, this logic is reduced from 16 to 8, and we can now use an 8x1 mux to implement this logic. These CR, CL, and L will act as our selection lines. After that, we are left with our this is just a flowchart that how things are going to work. These things I have shown you earlier. So this is basically how our PCB will look like. I have shown you my PCB, and let me show you a video in which you can see how this PCB is actually built. So after the PCB was actually built, we proceeded to the next phase, which was the final testing, and this is the pictorial representation of what our PCB actually look like. I have shown you in the video too. So this is the array of sensors that will be actually detecting the line, and this I used a variable to mount the sensors on to my car, and this is the actual robot or the car that we used to run on the arena. I will show you the working and the robot actually following the line on the arena at the end of this presentation. So this was all the work. Now let's verify the truth table using some of the simulations. We will verify some of the combinations from the truth table and see what the output actually is. So if for instance we take this combination 0011, this is my circuit, as you can see. So 0011 basically means that this is the left sensor, center left, center right, and the right sensor. So 000011 in the truth table show that only the left motor is working. You can see that for 0011 the left motor is working, and for 0100 both the motors are working. You can see that 0100 both motors are working. So now let's test a combination like this: 1001, 1001. Now both of the motors are stopped. This is a condition that it may come if both of the center sensors stop working or are not properly calibrated. They will not follow the line, and they will have to stop. So the next combination, or the last combination I must say, let's try this one: 1111. In that case too, the motors should be off. You can see that in this condition 1111 the motors are off, and in this condition or this condition the motors are again off. You can see from the truth table I have selected personally this logic that if this condition comes, that 1101 or 1011 the motors should be off. So this was basically the project. This is the PCB layout that I use to make the PCB, and let's show you the video after which the presentation will end. Thank you for sticking by. Allah Hafiz.